Okay, for this last session as part of our node intro, I want to cover blocking I/O and non-blocking I/O. Recall from our functional and asynchronous programming discussion that there were 5 ways of adding or manipulating work on the queue, and we've talked about 5 through 2. So this session's about talking about the first one, making a blocking I/O call that ends up on a worker thread, or even asynchronous that ends up on a worker thread, or non-blocking, as it will. So let's talk about that and run through a few examples. So we did all this stuff, and then we're going to talk about blocking I/O and the event queue. Um, Blocking I/O is a common thing that you do in programs that blocks. Again, what we mean by blocking is as executions are, as instructions are executed, you get to a line of code that takes a while to execute and blocks the main thread of your running program. In our case in Node, a main thread is the only thread in a single threaded model. Um, so what we want to do is be able to work in Node's asynchronous way, if you will, to say that's a long running operation, so let's keep executing on our main thread and delegate the work off somewhere else, and come back to it later when that file I/O is done. All right, so that's why I included our diagram down here in the bottom. Again, we have the main event loop that has the work that Node's currently processing on it in that single process, single threaded model that we've talked about. And we're talking about is there a set of threads in the background, a worker pool. Typically there's 4 of them, although it's configurable on setup, to do this non-blocking I/O. We'll talk a little bit more about that. We'll talk a little bit more about what's truly non-blocking in here versus what's kind of non-blocking. Um, the the well, let's talk about it now. uh, and again, this is going to be a bit abstract what actually happens, but we'll get back to it. We'll go through a few through examples. Again, recognizing danger, blocking I/O, and that's the most common and typical thing that would block ahead of time. Node needs to know about it, so it provides its own special APIs, and it delegates the work of the I/O off to this thread pool, like we said. Now, this is a traditional thread pool in a sense. In fact, what it really is, when you look about it, is a library known as libuv, and this is an open source library. It is not specific to Node. This is an open source library that you can use in C, C++, and even your own environment. It provides this kind of asynchronous I/O type feature. But what's really asynchronous here? Well, what happens really in Node is that when your call executes on the event loop and it delegates off to the asynchronous threads, the event loop thread keeps executing, right? And this is still going on underneath. Now, if you know and understand the nature of I/O with your actual file store out in the subsystem, at some point blocking does happen. But now blocking is actually happening in the context of this thread pool. If you actually have too many asynchronous I/Os going on, more than this thread pool can handle, you'll actually have a different problem, even all the way back out in the event loop. But let's assume you have a sufficiently sized thread pool, not too many files open here, um, and that you're writing to the file system. At the low level, at the kernel level, what actually happens is the I/O call is going to block. That's just the nature of I/O with the I/O subsystem. Something has to wait for that subsystem to do its work, come back, give you the results. All right. So what Node's really providing through libuv and this thread pool is, it's in a way it's kind of a mirage. It's asynchronous at the node level because you can keep executing instructions and you can continue to do work in the event queue, but it doesn't change the underlying physical implementation, if you will, of the nature of I/O underneath. All right. Um, but we're trying to provide that consistent programming model. All right. Because it's special, because different things can happen, that's part of the reason we have things like process.nextTick. A lot of times when you'll use a process.nextTick or a set immediate timer might be when you do have some IO things going on and you still want to ensure some prioritization of things going in the event loop. But we'll get to that later. For now, we're just going to talk about the blocking IO APIs. All right, so let's go forward. Here's the API documentation, by the way, for Node 6.6. You can look at all these different calls on here. The examples I have in here are going to focus primarily on the common things that one would do, meaning opening files, closing files, reading files, and writing the files. Okay. Excuse me. All right. Now, you can do file I/O synchronously. So I'm assuming everyone has done file I/O and other traditional programming languages with blocking reads, blocking writes in a very sequentially oriented programming language. So, you know, there's going to be no real distinction when you look at code that looks like that. In fact, we'll take a look at that in a second as well. The async, but what Node provides by default is this asynchronous I/O, which is going to change the APIs up a little bit. So even looking down here at the bottom of the slide with our first APIs, open and close. All right. First, when you use just file system, I should point out the module here, the package is FS for file system in Node. It's built in. You don't have to include anything third party. It'll be part of your standard Node installation. When you make a call with just open or close, and you'll see this with read and write, by default you're doing asynchronous. All right, so in the asynchronous part, you're going to provide this callback, as we've seen in other aspects of Node programming, and that callback gets executed when the work returns back to the event queue from that delegated thread pool. All right, now, but by default you have sync versions available as well. This bracket sync means that this is optional. So if you include that, then you also have availability of a synchronous API, but then the callback goes away. All right, so let me jump over and let's take a look at just reading a file in Node and what that looks like. So this is file read sync in your code repository, example from Brad Daly. And you know, outside of just the nature of the APIs, if you just look at the sequence of execution here, we're executing in a synchronous mode now. This is not Node's asynchronous capability. We are using the synchronous version. We require our file system module. There's file system open sync. All right. There's a sample data file that comes along with your code. It's in read mode and so forth. So this is just a synchronous call. Notice there's no callback over here. So this is going to block until the open is complete, and then it's going to go forward and synchronously execute. This is actually using a version of the read operation that reads a certain number of bytes. In this case, we have a buffer that's 5 bytes long, and there's no callback here again. All right, that's the point in the read sync. We are executing sequentially. We're going to go one by one, execute each line, and we get to this read sync. Now we're only reading 5 bytes. When you run this, it's not going to feel like it's blocking because it's going to go very fast. But the point being is that it could block, or it actually technically does block at a very low level, meaning, you know, execution does not continue onto this console.log until read sync completes. All right, so this is just a do while loop that reads until the end of the file, and then the same thing with the close sync here. That's going to block before the veggies line comes out. So if we went in and modified that code to introduce some kind of artificial sleep, you would see it takes quite a while to return. All right, but that's the nature of traditional synchronous I/O in Node. Now, what does it look like when it's asynchronous? All right, pretty much the same program, right? But just written in this asynchronous fashion. In this case, we're not at the top level. We're defining a function to read fruit. It will read in a buffered fashion through 5 bytes. And oh, here's our callback function. All right, that callback function is going to go through and execute when the subsystem comes back. If there happens to be an error, and this one's not handling the error case, if there happens to be an error that's returned, it'll actually be bound to the first parameter, and we should be checking that. We'll check that in other examples. But for now, we're going to assume we're executing okay. The bytes coming back is the second parameter. And we're adding things to our third data parameter, which is one we're going to pass in. All right. Excuse me. Notice as well that this is recursive. It's calling read fruit again, so it's going to effectively, we got rid of the do while loop by making it a recursive function to read this number of bytes until the number of bytes we get is not greater than 0, so there's no more data, and then we'll execute the close. So again, the close here actually could have a callback on it as well for the error function. It doesn't, but notice the open down here. Right? This is just declaring the function, by the way, right? It doesn't execute. Initially, it has to be invoked. Where is it invoked? Well, on the open, right? Again, no sync here, so this is an asynchronous call. Indicates the file, indicates the modality, and here's our callback function, indicates whether there's an error or not, and to go ahead and call that read fruit the first time with an empty initial fruits buffer, and then goes through and does our recursive loop. All right. These are examples are in your code. So there's your file read and how many bytes are written out each time, and then there's the asynchronous. Oh, that's not the right one. I'm sorry. This is async version. Okay. The other example that we have up here actually does a full read file. So in that first example, we were reading into a buffer, right? Now, again, why would buffer I/O matter on such small files? Well, it really doesn't, right? But you can use APIs that read the entire file. So this one is an asynchronous, all right, read file is an asynchronous API that reads the entire file, all right, and checks if there's an error. So this is actually more proper code than the other example, because we actually check the first parameter that comes back to see if there was an error, and if there was an error, then indicate some appropriate message, take some appropriate action. However, this one reads the entire file. Notice how we have no open and close here, because as an API that reads the entire file, the open and close are implicit. It's going to do that immediately, but it's still asynchronous, right? So it's not going to do the close until you get back. Over in our buffered I/O example, why may this be a good practice? Well, again, think hypothetically. Say you're web developer who's got to output a large, you're writing back to the response stream a large media file of some kind that's going to go down to the browser. If we read file of the entire thing, one is we are assuming heavy load on the server side's resources to do the I/O, as well as the memory needed to buffer internally and write that back out to the response stream. In fact, it might read that whole file into memory. Second is it might take a relatively long time. Now again, we may be operating asynchronously. We've delegated that off to a worker thread, but it still may be an inordinately long amount of time from a web throughput perspective and a web response time perspective for us to do that. Whereas perhaps we want to check more frequently on updating the user, right? So imagine a file read progress bar or something like that. So we can buffer very large output, and I mean, megabytes, dozens of megabytes large, into a buffer, make more efficient use of our internal memory, as well as have an opportunity to give a status update or perhaps even partial rendering back to the browser as part of a response output stream. Okay. Going forward. I lost my... Okay, sorry. You can probably tell from my scratchy voice I was about to have a coughing fit. I had to go get a drink of water, so let me continue. Just to be complete, there are write operations that we can look at. So the entire write file, for example, no open, no close. This is asynchronous. There is a synchronous version, but the asynchronous, you could tell because the callback is here. Checks for the first parameter error condition. indicates whether the write succeeded or failed. So that's how you would effectively check whether or not your operation was correct and completed. There's the synchronous version of a write. This looks just like the read version. We have our open sync and our close sync, and then we have our write sync in a buffered way. This one's going through the array as it's buffering as opposed to using bytes. And it goes ahead and writes out that many bytes depending on the size of each one of these. But again, no callback required on the synchronous write. And just like the read async, there's a write version of these things as well. Again, we have a write operation that works recursively by doing its write, binding a callback to the completion of the write, checking whether or not the write worked okay or not. If it did not, it indicates the write failed. If it did, it indicates how many bytes, and then eventually does the recursive call again. And then again, we have our asynchronous close operation. If there was no length associated, or meaning no more elements left in the array as we did recursively, and then we start the whole process by opening the file. And again, here's a nice distinction. Let me slow down here for 1 second. If you look at write sync, right, classic synchronous I/O, right? And we open the file, we do our reads and writes, we close the file, right? That's the order in which we go. In an async, we open the file, but the chaining of the next piece of work happens via callback. So again, we're going to execute this, but then we're going to put the callback on the event queue as something that happens when the open operation returns. I don't know. Lost my place. There we go. What's going to happen with that open? It's going to be a piece of work on the event loop. It's going to be delegated to the thread pool. The thread pool is going to talk to the I/O subsystem, come back, and basically give an event that then will trigger the execution of this callback. Now, you run each one of these examples, you're not going to notice, a difference. If I do node file write for the synchronous one, and that's the full write file. If I do the sync, looks pretty immediate. And if I do this one, because we're dealing with small amounts of data. But again, it's going to matter more when you do really large amounts of data and you want to indicate or have some access to executing events and not blocking everybody else. Again, it's part of being a well-defined or well-behaved best practices node program. All right. So those are the read and write. You also have access to some file metadata type examples. So we can also look at, let's see, file stats is one of them. And what does this do? There's actually a stat API. It has a callback, so it's asynchronous. It indicates based on the file, if no error, starts printing out a whole bunch of stuff about the file. So in this case, it's doing it about the file stats program itself. That's the one that's opening up. So when you execute it, it kind of gave you a nice little stringified JSON to, where you get a JSON object back, and then it stringifies it so it can print it out. Tells you things about the file, and again, it's what it actually did it on was itself, filestats.js. And notice though some things that are interesting in the metadata down at the bottom. It indicates whether it's a file, it indicates whether it's a folder or not. So just like other file handle APIs in other languages, including Java, you can query whether a particular file handler you're looking at, or file descriptor I should say, is a directory or a folder, or whether it's a regular file. You can also ask whether it's a socket, whether you're reading off a network port or not, because again, I/O is I/O from the subsystem perspective, whether it's coming from the file system or whether it's coming from your network stack. Okay, so that's the kind of things it's asking for down here. Excuse me, I'm still dealing with my cough. Okay, so again, there's a large number of APIs here that you can look at. Most of these APIs should be familiar, and exist. Say, working with file permission, changing, changing ownership all these kinds of things that you should be used to doing in whatever language you're most comfortable doing in I/O. The real thing is when you look here, you see in a lot of cases sync and async versions of the same APIs. The sync versions, again, at the node level block, and they are not the default. Node wants to use asynchronous by default, which is why you have to put the sync at the end of these things, all right, the APIs when you want to be synchronous. Um, Realize from our computational perspective that we are better being asynchronous. It's what Node wants you to do because you are a better player in this world. But and also in a web development world, it increases throughput because when you block on in your work, you're blocking everybody who's got work on the queue, so you're not well behaved. And then the last thing to caution you about is don't use asynchronous and synchronous APIs at the same time. That gets you into really strange, non-deterministic, and usually error-prone types of behaviors. I mean, imagine if you're trying to, let's say, open in an asynchronous fashion, and then write in a synchronous fashion or something like that. You may actually wind up trying to write to a file descriptor that you haven't received back yet from the asynchronous call in situations like that, and you can get into yourself into a lot of trouble. So asynchronous is preferred over synchronous, and never mix and match the two APIs. You'll get unpredictable results. All right. The final one you can type of file I/O you're looking at. So all the file I/O we've been talking about so far is kind of has analogies that I hope you're comfortable with in another language, right? Reading and writing an entire file or doing buffered I/O at your application level. You can also treat I/O as a stream. If you're not familiar with streaming, it's certainly relevant in web programming and become more popular with more media style implementations. Um, Basically, streaming gives you an API layer that you know, like even think of the examples that we're just doing with buffering. We're kind of handling our own buffering and reading in of things in our own internal events of when the buffer gets full and so forth with those recursive calls. Streaming I/O kind of gives you a more logical API for dealing with I/O that's kind of coming into your application space in a more continuous way, if you will. Um, so Node provides a stream module to do these things. They can be very useful when reading. So we'll see later, I haven't gotten to it yet, an example where we'll be reading the payload of a post. That's a file upload using a streaming I/O to read from our network socket. And likewise, when I was giving you the example before of writing out a large file, maybe a large media file to your response stream back to the browser, of doing that in a buffered way. You can also, and probably more naturally, use the streaming API to write that data out to response. It basically just gives you a better abstraction. Notice here, I mean, it's streaming is not a different physical implementation. The I/O subsystem and the way it works is the way it works. You're providing a conceptual API that seems, probably a bit more natural to the way things work by providing an API that works through an event mechanism to tell, when data has been read in, when it's written, what its status is, and so forth. So the API looks a little bit different. In fact, these examples from the book are a little bit more involved. Also notice that these examples, I'm looking at file read stream and file write stream, do this thing that we saw even with events of indicating an inheritance. All right. So this indicates that this answers object is going to inherit from stream.readable. And when we do that, notice that we are inside the constructor. We invoke the readable part with the call that, again, basically is like our super call we talked with event emitter. Goes over and invokes that part of its constructor. So we've initialized the full range of our object by initializing the readable part together with our own answers part. And then we can also manipulate the prototype again to indicate its underlying private read function in order to give us custom behavior about what we want to do. In this case, reading through a particular set of data values. All right. This one again, this will execute just fine, but you really need to kind of walk through how that works, and it basically gives you some information, some meta information back. And there's also a write one that tells you the write one reads, or I'm sorry, writes through a set of environments with um, a different kind of thing going on. Again, notice it specifies its callback. It's pushing data. Those are the items that you saw on the output, and even recursively calls its callback until it's done. All right. So that's in a nutshell. I mean, these specific examples aren't as important as understanding a streaming perspective to I/O. Streaming APIs have become more popular with the web, especially as the web has started to go from being from being text-based to dealing with far more large media files of different kinds. Streaming APIs tend to make more sense in these modalities. Right. So this is the last recording in our Node intro from a code perspective summary. Um, we're just getting started. The point of this was trying to get you to embrace the functional programming paradigm, embrace the asynchronous model. That's why we went through 1 through 5. I understand with kind of simple toy examples, it takes a bit getting used to where these mostly are useful. Um, you should be, one of the things we'll be evaluating with your programs and as you develop best practices in Node is, again, trying to keep things modular, try and keep your computational tasks discrete and short, try and use the asynchronous APIs with I/O or really anything else. Get used to this notion of chaining your callbacks so you kind of get that semi-sequential feel. We saw that with you saw that with the open followed by the write and read operations, but also realize that you can't assume strict sequentiality in the sense that it's going to just be the next call. It's going to go on to the event loop, the event queue. The event loop's going to pick it up in turn. So essentially, you're getting this pseudo concurrency across multiple requests being handled in your web application space, basically interleaving via these asynchronous behaviors, and you have to kind of really consider in your mind what it means to be correct in that model. You're just not executing something line by line. You're interleaving work on a single thread across multiple parts of the application. So it gets very confusing, and you kind of take out a piece of paper and kind of write down the interleaving possibilities and understand when you're doing things like asynchronous I/O across multiple different HTTP requests coming in all in the same event loop, or even just be very careful about anything that would be considered global data, a global variable, a global array handling data. Right? You have multiple HTTP requests perhaps coming in and manipulating that. But what happens? What happens when there's interleaving operations being performed, each one logically belonging to a different HTTP request, but all of them sharing data? And even though you're single-threaded, it starts to feel like a multi-threaded environment, and it should kind of make you think of thread. How do you program in a thread-safe manner? Well, what does that mean? We don't have threads. We don't have a synchronized block. We don't have these explicit concurrency mechanisms. So how do we deal with things like that? I give part of the punchline is, well, first of all, you try and avoid them and do things more local to your piece of work in this functional module so you can stay nice and encapsulated. But even so, there may be situations where you simply can't, right? When you have to use a shared file across multiple requests, and what can you do? So we'll be talking about those things as we move next to the low-level HTTP module. So keep in mind the ways you can manipulate the asynchronous event queue to resolve these problems. Okay.